Hello and welcome to this first entry in our series on the material synthesis of weakly coordinating anion salts. My name is Philip and I want to show you how you get easy started with weakly coordinating anion chemistry. To do that, we will discuss the one-pot synthesis of the lithium salt of the tetrakis perfluorobutoxyaluminate anion, which is shown here. The lithium salt can be simply prepared from commercially available starting materials, namely lithium aluminum hydride and perfluorobutanol. The reaction takes about 2 days and can be scaled up to about 250 grams. In our lab, we usually do reactions yielding 80 to 140 grams of the lithium salt. The reaction is quantitative and gives us the product in up to 97% yield. Starting from the lithium salt, a lot of procedures have been developed to yield weakly coordinating anion salt with other metal salts, with strong oxidants, with acids, as well as with organic cations, which can be used for electrolytes and ionic liquids. To learn more about the synthesis and the use and application of the salts, we refer to the original paper as well as more recent reviews on the topic. So now, on the following slides, I want to present you a step-by-step synthesis from purification of the starting materials to the final analysis of the product. The preparation of the lithium salt demands for the knowledge of standard Schlenk techniques. If you are not so familiar with Schlenk techniques and the high vacuum line, we will refer to Andrew Burry's paper on standard Schlenk techniques. Here you find everything you need to know to get started on your Schlenk line. Additionally, you should know how to sublime your end product under an inert atmosphere and how to work at a glass box. So now we can start with a checklist on our glassware. For the purification of lithium aluminum hydride, we need two 250 milliliter one-necked Schlenk flasks. As a reaction vessel, we will use a 1 liter 2-necked Schlenk flask with a magnetic stirrer. Additionally, we will need a spiral or Graham condenser, a dropping funnel, and a gas bubbler. For a final purification, we need a sublimation apparatus. Now we go to the chemicals. Here we need, of course, both our starting materials. Here we use lithium aluminum hydride, which we purify as described during the next slides. Additionally, we need our perfluorobutanol, which will be dried over pentoxide. This will also be described in the next slides. For the purification of lithium aluminum hydride, we need very dry diether. Finally, as a solvent of your reaction, we use dry hexane or heptane. The quantities of the reactants used in the example showed in the next slides are written here. Our end product was 131 grams of the lithium salt. So let's start with the purification of our starting materials. It is very important for the reaction to thoroughly dry our perfluorobutanol. As a drying agent, we use pentoxide. To dry our alcohol, we fill the alcohol as well as pentoxide into a storage vessel. This should be left to dry for at least 1 day, preferably a few days. Then we perform a static vacuum condensation to condensate our now dried alcohol into a new storage vessel. The setup for this is shown here. We attach the condensation bridge as well as the new storage vessel to our vessel with the alcohol and the drying agent. Then we do a freeze pump froth cyclization on the alcohol. In the next step, we condense it over by using a dry ice bath with CO2 and isopropanol, or by using liquid nitrogen. More details on this sublimation condensation procedure can also be found in Andre Borys' paper in Organometallics. At the end, we have an alcohol which is now very pure and dried and ready for our reaction. In the next step, we look into the purification of lithium aluminum hydride. Unfortunately, lithium aluminum hydride is metastable at room temperature. Hence, it decomposes to form aluminum, dihydrogen, and lithium hydride, as well as other products. This is not good for our reaction, and hence we should purify the LaH. But if you have old gray samples of LaH, you can still use it after a simple purification process. To do that, you use your old gray lithium aluminum hydride and put it into a Schlenk flask. Then you add approximately 20 milliliters of dry ethyl ether. You should let this mixture stir for a few minutes and then do a filter cannulation. After the filtration and the evaporation of the diethyl ether, you should get a nicely colorless and very clean purified lithium aluminum hydride. This can be easily used for the reaction. Another way to get a very pure lithium aluminum hydride is to buy a commercially available solution of LaH in ether. Here it's important to not buy a THF solution because the THF will coordinate the lithium in the LaH. To store your purified lithium aluminum hydride, you should use a freezer in a glove box. In our experience, it is stable for at least 1 year at minus 35 degrees. When we now have obtained our very pure lithium aluminum hydride, we have to prepare it for a reaction. For the reaction of this lithium salt of the weakly coordinating anion, it's very important that the lithium aluminum hydride is a very, very fine powder. Hence, we should grind it for at least 15 minutes, preferably on the day before the synthesis, in a glove box. You should definitely only grind lithium aluminum hydride in a glove box because you will get hydrolysis outside the box, and also if you grind it on air, there's the risk of an explosion. After the purification of our starting materials is completed, we can now look into the preparation of the glassware needed for the reaction. Here, it is important to heat our glassware in a high temperature oven overnight. Concerning the condenser, we strongly prefer to use a Graham or spiral condenser to achieve a very effective cooling. Another cooler condenser which can be used is a vertical intensive cooler. We strongly discourage using a Liebig or a Dimroth condenser. Additionally, we need a dropping funnel to add our alcohol to the reaction mixture. Finally, we should use a round bottom flask, which also should contain a magnetic stirrer. As only one additional glassware is the bubbler, which does not have to be heated overnight in the oven. Since we have purified all our starting materials and prepared all our glassware, we can now look at the of the reaction and how to set up the reaction apparatus. As a first step, we go to the glove box and weigh out a purified and finely ground lithium aluminum hydride into our reaction flask. This step can of course also be done at the day before of the reaction. Then, during the same time, we attach our other glassware to our high vacuum line. So we attach the condenser with our gas bubbler, as well as the dropping funnel separately to the high vacuum line and additionally heated with a heat gun under vacuum. Then we take the reaction flask and also connect it to the vacuum line. This is shown in the middle here. Finally, we add dry hexanes and heptane to the lithium aluminium hydride in the reaction flask. Here, approximately 100 milliliters of solvent should be used per gram of lithium aluminium hydride. Importantly, you should not use pentanes but solvents with a higher boiling point, such as hexane or heptane. In the next step, we assemble the reaction apparatus. This is shown in this picture here. Under a stream of argon, we attach the dropping funnel to the reaction apparatus as well as the condenser. Then we add the perfluorinated alcohol to the dropping funnel. Finally, we attach the cryostat and cool our condenser to -30 or -20 degrees. This is important to ensure that none of the alcohol is lost during the evolution of dihydrogen in the reaction. Then we can finally start with the reaction. Here, we add the alcohol dropwise through the dropping funnel to the reaction mixture under a constant steering. This takes approximately 30 minutes to 1 hour. Here, we should ensure that we have a steady stream of dihydrogen, which is not too extreme and should be approximately 4 to 5 bubbles per second. After all the alcohol has been added to the reaction mixture, we reflux the reaction for 5 to 6 hours until the formation of the hydrogen has almost stopped or at least significantly faded. During this time, we see a precipitation of a lot of colorless solid in the reaction mixture. As a small lab hack, it is always good to attach a paper towel here to prevent the ice or water coming into the hot oil bath beneath it. Then, after the hydrogen evolution has stopped or at least significantly faded, we let the reaction mixture cool down to room temperature. Finally, we disassemble the reaction apparatus, close the reaction flask, still under inert gas, and put it under freezer at -30 degrees overnight. During this time, we see a lot more precipitation of a white solid. And the next day, we can simply remove the solvent via filter filtration. Then we should dry the remaining solid thoroughly under a high vacuum to isolate our lithium PF. To simply test for a complete conversion, we can add a small spatula of the colorless powder to water. If we still see some gas evolution, this is a strong indication that we have unreacted lithium aluminium hydride in the mixture. What we can do then is add hexane or heptane as well as a few milliliters of the alcohol and reflux the mixture again for 1 to 2 hours until we don't see any dihydrogen evolution anymore. The product should be further analyzed by NMR and IR spectroscopy. The NMR can be performed in deuterated chloroform or deuterated dichloromethane. Here it's often beneficial to add a few drops of the ether to increase the solubility of the lithium salt. In the NMR, characteristic signals of lithium, fluorine, and aluminum can be detected. Further information can also be found in our original publication. The IR spectrum of a variety of salts of the perfluorinated aluminate anion are discussed in the chemistry paper of 2009 from our group. If we have seen some impurities in our end product and want to ensure a very high purity, which is especially needed for electrochemical applications, we can easily sublime the lithium salt. To do that, we fill the colorless powder under inert atmosphere into a sublimation apparatus, and then we sublime the product at 80 to 100 degrees under a dynamic high vacuum. Here it is good to cool the cooling finger to -20 to -10 degrees Celsius to ensure that the product is not falling off the cool finger when we dismantle the sublimation apparatus. It's very important to not heat the powder above 120 degrees because at this point the lithium aluminium hydride can decompose exothermically in an explosion. At the end, we should get a colorless, nice powder of a pure lithium salt. Thank you very much for your attention. We hope that this tutorial has been helpful and gets you started into the beautiful world of weakly coordinating anions. If it has been helpful for you and you find it useful for your publication, then please cite the original paper as well as this tutorial presented here. If you have any questions on the synthesis, follow-up chemistry, or anything on weakly coordinating anions, feel free to reach out to us. Thank you very much.